chemical thermodynamics, energy, free energy, entropy, free energy, and equilibrium. So, chemical thermodynamics. What is chemical thermodynamics? This is the chemistry that deals with energy exchange, entropy, and the spontaneity of chemical process. This is a chemistry that deals with energy exchange, entropy, and the spontaneity of a chemical process. This might not sound so easy now, but as we go on, you get to understand what we're talking of. So we look at thermodynamics versus kinetics. Kinetics tells us how rate of a reaction depends on the pathway from reactant to product. How rate of reaction depends on the pathway from reactants to product. That is from where you start, the reactants you put together to react to give you a particular product. So the rate tells us, it tells us of, the kinetics tells us how that rate of that reaction depends on the pathway from where you start reacting those reactants to where you get to the final product. Whereas thermodynamics tells us whether a reaction is spontaneous based only on the properties of reactant and product. What do we mean by spontaneous? This is whether it's telling us whether the reaction will take place just on its own, effortlessly, without you having to put in any force to make it to happen. And as we go on, we'll explain this. So now the thermodynamics is built upon the fundamental laws that heat and work obey. Is a branch of physics. Thermodynamics is a branch of physics. It's built upon the fundamental laws that heat and work obey. We will see those laws. So in thermodynamics, the collection of objects on which attention is being focused is called system. I'm going to explain and give you an example. For instance, a human being is a system. Let's say we are studying a human being. Then what you're studying is the system. So the collection of objects on which attention is being focused is called the system. Or you can take maybe the room where you are. If that is where you're studying, if you're studying everything about the surrounding. So for instance, if a human being is what you're studying, a particular person, then anything outside that body is the surrounding. Anything outside that body is the surrounding. So while everything else in the environment is called the surrounding, the system and its surroundings are separated by walls of some kind. What those of the engine block, and those are called diathermal walls. We'll go into that later. So what do we mean now? Let's take the system. For instance, the system is a human being. What you're studying is a human being, a body, person. The system is a person. The outside environment where the person is a surrounding. And there is something that is separating the surrounding from the system. That is a wall. In case of a human being, the skin, the outside skin, is the is the wall that is separating the system from the surrounding. A room, and the room is your system, then the block, the wall of the room is your wall, and the outside environment is your surrounding. I believe you understand this. As we go on, you should understand. So now, all those, we're looking at the symbols of the different things we're going to look at. We're looking at internal energy, we're looking at entropy, and so on. So for internal energy is designated by a capital letter U. That's the symbol for internal energy, capital letter U. For entropy, all this we will see and understand them very soon. Entropy is designated by capital letter S. So combining U and S with P, pressure, temperature, and volume, it gives you enthalpy, which is designated by capital letter H. So you can now relate pressure and temperature and internal energy to enthalpy. So we have here this relationship, H is equal to capital U plus PV. That is enthalpy is internal energy plus pressure times volume. So this is another parameter you'll come across. Gibbs energy. It's another property you'll come across in this study. Gibbs energy is designated by capital letter G. And you have a relationship here. G is H minus TS. H is enthalpy, T is temperature, and then P, pressure. So Gibbs energy G is enthalpy minus temperature times entropy. So we have also, you will come across delta H is related to heat absorbed or released at constant pressure. At a constant pressure, you don't change the pressure. At a constant pressure, the heat that is absorbed or released is related to delta H. So you will know that is, we subtract the two different heats absorbed and released, and then you will get the change in enthalpy, which is delta H. Delta H is change in enthalpy. So G controls the position of equilibrium in closed systems at constant temperature and pressure. Very soon, I will show you what I mean by closed systems, open systems, and so on. So Gibbs energy controls the position of equilibrium in closed systems at constant temperature and pressure. So these are some important thermodynamic questions. What is the system? What is the surrounding? Energy is the ability to do work. I believe you all know that. Energy is the ability to do work, the ability to move or change something. So we have two types of energy. You have the potential energy and you have the kinetic energy. The potential energy is a positioned one, energy in position. Then the kinetic energy is the one in motion. Energy in motion is kinetic energy. Energy is the ability to do work. You don't have energy, your energy is not much, the ability for you to do work will be low. So the more the energy, the higher the ability to do work. So internal energy now. Internal energy is the sum of all possible forms of energy in a system. Is the sum total of all different types of energy in a system. As we go on, you will see the different kinds of energy, and now you sum it up, and it's called internal energy. You cannot measure internal energy. You cannot measure internal energy. Like I've said, it's the sum of the different kinds of energy. So you will sum it up to get internal energy. You're not measuring it. You can only measure changes in energy. You can measure changes in energy. Atoms, ions, molecules, all of them possess internal energy. That is the different kinds of energy all summed up together. That is the internal energy. So internal energy is independent of pathways used to reach that state. That energy itself is a state function. So it is independent of the pathways that you use to reach it. So state function, now we're talking of state function. So state function is a property dependent only on the state of the system. State function is a property that is dependent only on the state of the system. What condition that system is in, and not on the pathway. So it's dependent on what condition that system is, not on how you get to that system, not on the pathway. We're going to give you examples of state functions like pressure, temperature. They're not dependent on how you get there. They're not dependent on how you obtain the temperature or the pressure. They're not dependent on how you obtain them. So they are state functions. So, and then let's look at the system and surrounding. Like I've mentioned before, that the system is whatever is being watched. The system is whatever is being watched, whatever you are studying, that is the system. It's the repeating here so that at least it will get right into you. You'll be able to remember whatever you're studying, whatever is being watched, that is the system. And the surrounding is everything else outside that system. Everything else is the surrounding. We'll look at exothermic and endothermic energy. Exothermic and endothermic energy. You can see we're just going bit by bit, introducing the different properties gradually until later on you get into the real thing. So now exothermic energy is the heat transferred from the system to the surrounding. Heat that is transferred from the system to the surrounding. Exothermal is leaving the system and going out. Exo. So you will feel the heat. It is hot. The heat that is leaving the system and going out to the surrounding. So when you touch the surrounding, it is hot. Whereas endothermic energy is the heat transferred from the surrounding to the system. So the heat is leaving the surrounding and going into the system. If you touch the surrounding, it will be cold. That is the difference. Exothermic, exo going out, endo coming in. So now heat is designated by and the transfer of heat is measured in calories or joules. The transfer of heat is measured in calories or joules. Remember, heat is designated in this study, as you see, by small letter Q. Calories is the heat that is needed to raise 1 gram of water by 1 degree Celsius. Is a heat that you need to raise 1 gram of water by 1 degree Celsius. Joule is the SI unit for energy. 1 calorie is equal to 4.184 joules. All these you have to take time and study them because these are simple questions that can come out in your exams. Simple questions. How do you define calorie? And then how many calories, how many joules are in so how many calories? Those are things you should note. Okay. And we've talked of heat that is designated by small letter Q. Now, what is work? What is work? We want to look at this property, work, designated by W, small letter W. Matter, the ability to move or change something, the ability to move or change matter. Work on the system is positive, endothermic. You're doing work on a system, you're putting work on that system, so you're adding work on that system, so it's positive. Work done by the system is negative. The system is releasing work from itself, so it's negative. It's not adding to itself. When the system is adding work, the work is done on the system is adding, so that is positive, endothermic. When it is releasing, it's removing, it's exo, it's negative. I hope you understand that. So all this positive and negative that I'm showing you now, you will make use of it very soon. When you're calculating work done and on the system and work done by the system, you will need these signs, positive or negative, before you can get the correct answer. Because if you're asked to do some calculations, work done by the system, and you now carry endothermic and put positive, you will get everything completely wrong. And in calculations, when you're wrong, you're wrong. And so you have to take note of these signs. They're very, very crucial. They're very important. Okay? Now, change in energy. Change in energy is designated by delta E, capital E. Remember, I told you that heat is designated by small letter Q and work by small letter W. So what is change in energy? Change in energy is the sum of heat and work. Adding heat and work, that is the change in energy. And that relationship, you have it as delta E is equal to Q plus W. We have an example here for you to view in exam. During a process, 4.5 or 45.0 joules of heat, I told you joules, heat is measured in joules, calories, was added to a system. 45.0 joules of heat was added to a system, and the system did 155 joules of work on its surrounding. What was a change in energy for the system? What was a change in energy for the system? So the change in energy is what we're looking for. And remember, change in energy is delta E, and it is equal to Q plus W. So now, Q here is given to us as 45.0, and W is given to us as 155 joules. And why we're putting minus here, they say that the system did work. The system did work. So it is carrying minus sign because the system did work. It's not work that was done on the system. It's a system that did the work. So it's carrying minus sign. So if you now take the change in energy, delta E is 45. W is minus 155. You add it together, you will have minus 110 joules. And what is that? Because that change in energy is minus, is exothermic. Is exothermic. You remember what I told you before? It's minus, so it's exothermic. If it is positive, it is endothermic. If it is negative, it is exothermic. So you can be asked a question like this, calculate it, and then what do you have there? And you will write, and then you'll be asked, what is it, exothermic or endothermic? Also, you should be able to also know using the signs. That's why I say that the signs are very, very important. If you miss the sign, you miss the value, you miss everything. Okay, so we go to enthalpy. Enthalpy is the heat content of the system. Is the heat content of the system. So now delta H is the change in enthalpy. That means the change in the heat content of the system. And you have the relationship with the delta E and the delta H, change in energy and the change in heat content. So the change in heat content is equal to the change in energy plus the change in the product of pressure and volume. Change in heat content of a system is the change in energy plus the change in the product of pressure is negligible. It's only considerable in gases. In liquids and solids, change in volume is negligible. If you heat a solid, you make it to change, the change of its volume is negligible. But if it is in a gas can easily spread and the volume changes. So when we're looking at dealing with solids and liquids, we will neglect, we remove the change in volume. But when we're looking at gases, we will consider the change in volume. So if it is liquids and solids we're looking at, now the change in enthalpy, the relationship will be different from the relationship change in energy. When we're looking at liquids or solids, the enthalpy change will simply be equal to the change in energy because the volume is negligible. If the volume is 0, you multiply the zero with the pressure, it is 0. So that is how that one is wiped off when we're considering liquids and solids. But when we're considering gases, that change in pressure times volume is considered. So change in enthalpy, we're still talking of that. If the products have more energy than the reactants, the change is positive. If the products have more energy than the reactants, the change is positive. because you will always subtract the reactant, the energy of the reactant from that of the product. So that is why you will have the change positive. And so that is when you will now have endothermic. Your delta H, the change in enthalpy, will be positive. But if the product has less energy than the reactants, the change will be negative. Why? Because we always subtract at any time, you will subtract the reactants from the product, the energy of the enthalpy of the reactant from that of the product. So if the product has more energy, then you will have the change as positive. But if the product has less energy, then you will have the change as negative. When the change is positive, you have your enthalpy as endothermic. When the change is negative, that is when you have the energy of the reactant more than that of the product, then you have exothermic as enthalpy. Okay? And so let's say entropy. What is entropy? Entropy is a measure of disorderliness of a system. Measure of disorderliness in a system. So entropy, I mentioned to you, is designated by capital letter S. So the change in entropy, when the change in entropy is positive, it means there is increased disorderliness. When the change in entropy is positive, it means there is increase in disorderliness. For instance, when you're melting ice or something is burning. So then we will still talk of spontaneity later. Like when you're melting ice, you just bring ice and drop somewhere, ice cube. You don't need to do anything. It will start melting. It will no longer, that cube will no longer be in order. It will just melt off, and then there's increase in disorderliness. That is the entropy, a change in entropy is positive. Then on the other hand, when there is decrease in disorderliness, if you have that thing that has melted, the ice that has melted, and now when it melts, it gets disordered, the structure, everything. But you now carry it back, put in the freezer, and then you decrease the disorderliness. This is freezing. It now stays intact. It's not scattering again. Then the entropy change in that case is negative. So when the entropy that you will see in your exam, you know, you're doing CBT. So these are the kind of questions you will see in your exams. You can be asked, if entropy, change in entropy is negative, what does that mean? Is that decreasing in disorderliness? Is that increasing in, you know, it can be confusing to you when you're in exam hall, but when you have looked at it and you really understand it, not just quoting, you understand it, then it will be very easy for you. Okay? So now, what is thermodynamics useful? Why is it useful? Why is thermodynamics useful? Why do we need to study it? The thermodynamics give us qualitative explanation of materials behavior. Gives us qualitative explanation of materials behavior. Another usefulness is that it gives us quantitative understanding of material status. Quantitative understanding. Qualitative, you just know it. It's nothing that you can count. Quantitative understanding is something that you can, you know how much, how many. Quantitative understanding of material status. Then also, thermodynamics gives physical significance of thermodynamic functions. it gives physical significance of thermodynamic functions. You will see some thermodynamic functions and as we go on. So application of thermodynamics. Thermodynamics is applied in extraction, in refining. It's even applied in corrosion studies. It's applied in phase transformation, phase diagram calculation. It's applied in materials processing. It's applied in design of new materials. So thermodynamics finds applications in several processes. So even in human body, thermodynamics is applied, that, like I told you earlier, that you can study human body as a system and a lot of things, so you use thermodynamics to even understand a lot of things in the human body. In air conditioning system, like in car radiator, even in power. So you apply thermodynamics in all this. It's fine. Thermodynamics finds its application in almost everything. So now concept check. Let's check this. Consider 2.4 moles of gas contained in 4.0 liters bulb at a constant temperature of 32 degrees centigrade. This bulb is connected by a valve to 20.0 liters bulb. Assume the temperature is constant. What should happen to the gas when you open the valve? I think I'll show you a picture that will make you to understand the question. So if you connect two bulbs, this one contains 4.0 liters of gas at a temperature of 32 degrees centigrade, and that temperature remains constant. We want to finish this time, so let me finish, then we'll see how we can go back to questions. Okay, so let's be done with the lecture first, then we'll look for time for the question. So if the temperature remains 32 degrees, connect another bulb to the bulb that contains this 4.0. So what do you think will happen to the gas when you open the valve that that link these two bulbs? So now, sorry, the other one is calculate delta H, delta E, Q, and W for the process you described above. Calculate delta H, delta E, Q, that is the change in enthalpy, change in energy, heat, and work for the process you described above. So all are equal to 0. No work is done, no change in enthalpy, because no change in temperature, no change in energy. We are told here that the temperature remains constant. So the temperature is 32 degrees centigrade, there's no change. So when there's no change in temperature, there's no change in energy, there's no change in enthalpy, because everything is linked with the heat. So you end up having everything equals 0. So, and then give your answer to part B. What is the driving force for the process? What is the driving force for the process? The driving force for the process is entropy. We just keep something, it will get disordered on its own, spontaneously. So disorderliness, you just connect this bulb, the one that has 4.0 liters, connect to the other one that is empty, you just leave it there. There's no heat that is added, there's no temperature that is changed. So no change in entropy, no change in anything. So what is the driving force? It's entropy, disorderliness. Disorderliness increases here. So that's the force behind it. So let's now take time and look at. So a thermodynamic system is a part of the world that we have special interest in, like I mentioned to you before. So if we take, like we'll see here, this test tube. If we take this test tube as a system, or we're studying something in a test tube, and we have like this water bath. So now we have the system as a test tube. We have the surrounding as that water, and we have the universe outside, what is completely away from the system. And we have the boundary. So the surroundings, which can remain at constant temperature, regardless of how much energy flows into or out of them. The surroundings remains there at constant temperature. They are so huge that they have either constant volume, changes that take place in the system. Remains in this, in the surrounding remains constant. So now, thus, even though the system might expand, the surrounding remains effectively the same. Surrounding remains the same. The system might expand, anything can happen to the system, but the surrounding remains the same. So, now let's look at the different types of the system. We need to be able to distinguish between different types of system. I mentioned to you before an open system. So that we have 3 different types of systems. We have open system, we have closed system, and we have isolated system. We have open system, we have closed system, we have isolated system. An open system can exchange both heat and matter with its surrounding, and hence can undergo changes of composition. Open system can undergo changes of composition. I'm going to give you examples here. You can exchange heat, you can exchange material, anything comes in and goes out. That is an open system. But a closed system can exchange energy, but it cannot exchange matter. Can exchange energy, but it cannot exchange matter. For instance, if you cook food, put in your plate, not a flask, you put in a plate and cover it. It's a closed system. Within a short time or some time, depending on the temperature of that surrounding, along the line, the food will be getting colder because it's exchanging heat with the environment. Even though you have closed it, it will exchange heat, but nothing can enter into that system. Water cannot drip inside, nothing else. Anything that is there in the system remains what was there, the matter you put there. Nothing else will fall inside it. It remains, it only can exchange only heat between the surrounding and the system. That is a closed system. An open system It's open to exchange heat, to exchange matter. Anything can be put inside, anything can go, energy can go out, come in. But another system is an isolated system. Isolated system is a system that can exchange neither matter nor energy with its surrounding. It doesn't exchange anything. Of open system, closed system, and isolated system. An example of open system is a flask that is not stoppered and to which various substances can be added. A biological cell is an open system because nutrients and waste can pass through the cell, a biological cell. Nutrients can enter the cell, waste can leave the cells to be discarded, to be discharged for excreting. That is an open system. A biological cell is an open system because nutrients and waste can pass through the cell wall. You and I are open systems. We ingest, we respire, we perspire, and we excrete. It's a system. A human is an open system. We bring things inside, we remove things from ourselves, we exchange heat, we absorb heat, we exchange heat. Our skin can absorb heat, can exchange heat. So, system, an example is a stoppered flask. Energy can be exchanged with contents of the flask because the walls may. I just explained to you, if you keep your food in a closed plate, the wall can conduct heat. So heat will go out and come in, and so but the matter cannot go in and out. And another example is that of isolated system. It's a sealed flask, thermally, mechanically, electrically insulated from its surrounding. Like you have a water flask. That is an isolated system. You seal it very well. It is not the wall. The wall of it doesn't exchange heat with the environment. You can hold your flask, the body of the flask. You will not feel any heat. There's no exchange of heat, and the content also is intact. So that is an isolated system. So don't mix open system. Don't mix. And these are some examples that are shown to you here. For an open system, energy, matter can go in, can come out, and so on. You can see the food that is cooked, the water is going out, the matter is going out, and so on. Energy is coming. So everything happens in an open system. In a closed system, you can see your pot there. The water, the vapor is not going out. All those things are not going out. It's only the energy, the heat that is exchanged. And you see the isolated system there, your water flask, for instance. So we have another example here. Differences between individual types of chemical systems may be demonstrated using the example of making coffee. You want to make coffee, we can differentiate, we can use these differences now. The pot on a heater represents practically a closed system until the water is brought to boiling. You know, when you put water, put it on fire, it's a closed system, but when it boils, then it becomes an open system. At the boiling point, when steam is leaking from the pot, it becomes changing matter. The ready-made coffee kept in thermos flask, but represents a simple model of isolated system. So in this case, you have, before you boil, you put the water, before you boil, it's a closed system. It can still exchange energy. But when you boil it, it is opening vapor, the steam is going out. So it's changing and it becomes an open system. And then when you pour it in the flask, it becomes an isolated system. So now, phase, homogeneous and heterogeneous system. Let's see what is phase, what is homogeneous and heterogeneous system. The term phase is used for that portion of the investigated system volume in which its properties are constant in space, constant or just continuously changing in space. If a system behaves in this way throughout all its volume, we call it homogeneous system. It has just one phase. It has just one phase. You know what? Liquid, gas, solid, those are phases. So if the system has only one phase, it's homogeneous system. If a system contains more than one phase, that system is heterogeneous system. It can contain both gas and solid, and even liquid, gas, and solid. That's heterogeneous. So we're going to explain to you now phase and systems, and homogeneous and heterogeneous systems. Let's look at this example. Imagine that you have a bottle of whiskey. How many phases do you think that bottle of whiskey is consists of? How many phases do you think it consists of? Let's see the answer. So now, sorry. Let's see the answer now. You have a bottle of whiskey, how many phases? If we are, from the thermodynamic point of view, interested solely in the liquid content of the bottle, the system is homogeneous. It depends on what we're interested in. If it is only the liquid that we're interested in, that is the liquid phase. So the liquid has just one phase, it's the liquid phase. So that is homogeneous. It contains only liquid phase, which is a mixture of water, ethanol, and some additives. Whatever it is that is liquid, all mixed together, is homogeneous. It has one phase. But if, on the other hand, we're interested in the entire content of the bottle of whiskey, but not the bottle itself, then the system is heterogeneous. That means, remember that bottle of whiskey so with the litter containing air, the whiskey vapor. So that is two phases, containing gaseous and liquid phases. Remember when we were talking of before, the first one, whiskey, we're only interested in the liquid content. That is homogeneous. But when we are interested in the whatever is inside the bottle, whatever is inside the bottle is heterogeneous because we have the. Now, if, however, we focus our attention on both the bottle content, the bottle, everything, including the bottle itself, we also still have a heterogeneous system. But this time, the content, it contains other phase, like solid. That bottle is solid. So it's still heterogeneous. So we have the solid, the liquid, and the gaseous phase with everything together. That is heterogeneous. So I believe with this explanation, you're able to understand what phase is. You're able to understand also what and also what an heterogeneous system is. So want to look at thermodynamic process. Thermodynamic process. If the properties of a system change in time, it has, if at least one thermodynamic quantity changes, we say that a certain thermodynamic process takes place in the system. If the term process relates to a very broad range of most varied processes, from simple physical change like heating, various chemical reactions, up to complex multi-stage processes. So that's what process means. Simple heating, or even reactions, chemical reactions, or even combinations of several chemical reactions and different stages, you have processes. So individual kinds of process may be classified according to the several criteria. We have processes and we classify them according to what I want to explain to you now. We classify processes according to what we want to explain now. We have reversible and irreversible. We have processes at constant quantity. We have cyclic processes. What I mean by constant quantity is maybe the process at constant temperature, that is a quantity, or a process at constant pressure, that's another quantity, or process at constant volume, that's another quantity. So when we're looking at processes at constant quantity, we'll be looking at processes happening at constant temperature. We'll see what happens when we put the temperature constant. We don't change. We'll see what happens when we keep the pressure constant. We don't change. And we'll see what happens when we keep volume constant. But now, let's see reversible and irreversible processes. I think our time is almost up. I don't think we'll be able to go through reversible and irreversible processes. Let me see if we can just look at only that. Then we'll continue on the other processes in the next class. I think we can leave it. Okay. The cause of any process depends on the conditions under which the given system changes. So if we arrange conditions in such a way that the system is nearly at equilibrium, that is, the system can move forward and can move back at any, that consequently the direction of the process may be reversed by even a little change of initial condition. The process is called reversible or equilibrium process. A reversible process is thus a sequence of nearly equilibrium states of a system. So I believe you have seen some reactions that has that sign of reversible, this one pointing here and the other one pointing back at the point in a reaction, pointing front and back instead of equal to or one arrow. If you have one arrow going front, it means that process is irreversible. You add this reactant to this reactant and you have one arrow pointing front, it is irreversible process. It will just give you that product straight. You cannot do anything about it to go back. But when you have a process that is reversible, the sign is not given by one single arrow pointing one direction. It's given by two half arrows, one half arrow pointing back, one half arrow pointing front. That means you can change the situations, the conditions of that reaction to bring them back to the reactant side or back to the product side. It means you can make some changes of the conditions of the initial condition, so you can put it at equilibrium. So every reversible process is an equilibrium process. So reversible processes are equilibrium processes. Processes in the real world are mostly such that the system is out of equilibrium, at least at the beginning. So such process is called irreversible or non-equilibrium. They are one direction. So every irreversible process is also called non-equilibrium process. All reversible processes are equilibrium processes. Note this, you can be asked in a question in the exam. So an equilibrium process is just actually a splitting case of non-equilibrium process going on at the infinitesimal velocity. I think we have already overshoot our time. We're already at 9:01. And then let me see if I can quickly, okay, I think we will discuss this better in the next lecture. I don't know if it has been addressed. Do you want to ask a question? Okay. So we will call it a day today, and we'll meet again on Monday. So have a blessed weekend.
This one say thank you, mommy.
It's okay. So
See,
call it a day at this point.
this one is thank you, mommy. Thank you, mommy. Only say thank you, mommy. Thank you, mommy. I feel say
Okay.
thank you. Not guy.